my pleasure to introduce our keynote speaker, Professor Niels Schiller, Chair Professor of Psycho and Neurolinguistics and Head of the Department of Linguistics and Translation from CTU, University of Hong Kong. His keynote today is titled From Thought to Sound in Speech Production. Please join me in welcoming Professor Schiller.
Thank you very much for the organizers for inviting me. So when I was, just a short story, when I was preparing this presentation last week and the weeks before, I was thinking that this is a keynote, so I have 1 hour. And then I looked at the program last night and I saw I only have 30 minutes. So I thought, okay, I can do two things. I can speak twice as fast. Or I can remove half of the slides. So I removed half of the slides, and I hope that this shortened presentation will nevertheless be of interest to you. So I would like to tell you some of my work over the years in the area of not so much phonetics, but more psycholinguistics in speech production, which of course is also related in phonetics. And I started out as a phonetician and with phonetic research and phonological research, but then I also moved to different areas. So when we speak, we start usually with a pre-verbal message. That is, we have to conceptualize what we want to say, if we want to ask a question, or we want to express an emotion, or we want to talk about a dog, for example. The next step that we have to do in our minds is to access the lexicon in order to activate a lexical node that corresponds to the concept that we want to express. So in this case, a dog. Finally, we have to access phonological nodes in order to be able to put the word that we have accessed in the lexicon also in some form so that we can articulate it. Now, we can investigate this process in the lab by presenting, for example, pictures to participants and ask them to name the picture as fast as possible so that they have to engage in speech planning processes. And what we can measure in the end is a response. And this usually takes for a everyday image, it takes about a little bit more than half a second. So it's a fast process. And of course, the processes that we are really interested in are in the middle, in the speech planning, but we do not have direct access to it, right? Because they're happening in our brain, and so we can only infer what's going on in the brain. The first step, as I said, in speech production is the conceptualization. And according to this model by Pim Lefeld and his colleagues, this is also the first stage in their model. Of course, concepts are also have a semantic meaning, and a semantic memory has already been conceptualized like a network about 50 years ago by Collins and Loftus. And this is also one of the ideas that has been taken over in the Lefeld model, where concepts are being thought of as a non-decompositional unit. So they cannot be further subdivided, but they are connected with each other in terms of semantic categories. Now, this has gained some evidence also by neuropsychological patients with category-specific damages or deficits who are not able to name or make lots of errors in certain categories when they name them, although they are perfectly normal in other categories. Now, whether semantic knowledge is stored in our mind in terms of categories that are, or in terms of whether semantic knowledge is stored non-decompositional, or whether it's stored in semantic features is still not completely answered. a PhD candidate of mine, Yufang Wang, who will defend her thesis in a little bit more than a week from now at Leiden University, did some work on lexical, on semantic features. And what she found was that the number of phonetic semantic features that words share actually plays a role in the naming process. So she, in fact, has gained some evidence that it's not, if you see semantic representations as non-decompositional, that may not account for all of the findings that she had found in her recent work. The next step is lexical selection. So once we have conceptualized our dog, we need to access the lexicon. And so if we think about it in terms of a featural representation like this one, where you have several semantic features, for example, for legs, for tail, fur, and so forth, then you might think that several objects or several nodes in the semantic, in the lexicon might get activated. And that is also the case. So we know that when we want to say, for example, dog, we also activate cat, we activate horse, we activate donkey, and all these animals that sort of are similar to dog. But then we have to select, of course, the word dog, and this is because dog will get most of the activation from the semantic level. So we are finally able to activate our lexical node dog, our target node. How exactly lexical selection works, that's also a hotly debated question. So when we map the processes here on the right to the processes that have to take place in our cognition, you can see that lexical selection is basically a two-step process. There are two levels involved. One for lexical nodes. In the Leyfeld models, these are called lemmas, and phonological nodes. They correspond to two types of naturally occurring speech errors, namely word exchanges such as laboratory and my own computer. This is from Vicky Fromkin, and sound exchanges, on the other hand, such as children interfere with your knife light instead of nightlife. Whether this process, this two-stage process, is strictly serial, as claimed, for example, by Leyfeld, or rather cascaded or even interactive, as claimed by other models. So this is the Leyfeld model, where you have a strictly serial order of processes, whereas in the Dell model, for example, everything is interactive. All the levels, so the syntactic level, the morphological level, the phonological level, they are all connected with each other, and activation can go up and down in an interactive way. So which model is the best one is still hotly debated, but let me just show you one experiment carried out by Starrefeld and Lahaye a couple of years ago, where they wanted to investigate whether this process is strictly serial or not. So what they did is they asked participants to name pictures, for example, this cat, and in a so-called picture word interference paradigm. So you present the picture, ask the subject to name the picture as fast as possible, and ignore a simultaneously presented word. The word could be unrelated, like house. It could be semantically related, like dog. It could be phonologically related, like cap. Or it could be a mixed distractor word, such as calf, which is both semantically and phonologically related. And what they found was that, and this is a common finding, is that words that are semantically related, like dog, inhibit the naming of the target picture, whereas words that are distractor words that are phonologically related are facilitating. So you're faster. So here on the left, you see the response latencies in milliseconds. And now, of course, the question is, what would happen if the distractor word is a mixed distractor, like calf? so according to a strictly serial model, the two effects would be additive. So that means that when you take the reaction time for cap and you put the inhibition of the reaction time of dog on top of it, it should give you the reaction time for calf. However, what they obtained was a significantly faster reaction time. So what they concluded is that the lexical selection process is not strictly serial, but there is at least some cascading and maybe also some interaction going on. And this has been concluded also by other studies in the meantime. Grammatical encoding, that's the next step that the speaker has to go through when they are in the process of lemma selection. And I would like to illustrate this process a little bit by grammatical encoding. So this is a topic that I've been working on in the last 20-25 years quite a bit. So for example, in Dutch, words have so-called grammatical gender. So we say, for example, de tafel, the table, but also het boek, the book. So tafel, a table, and book have different grammatical genders, and these different genders are marked by different determiners. Grammatical gender is similar but not identical to what Chinese and Cantonese have in terms of classifiers. The classifiers are also considered to be lexico-syntactic features. In Italian anomic patience, Dante knew the grammatical gender of words in Italian, even if he could not produce them. So he could tell you what kind of gender, grammatical gender, a word had, even when he was not able to produce it. And when we are in the tip of the tongue state, so when we know a word but cannot produce it, it has been shown that speakers, when they are in such a TOT state, also know the grammatical gender of words more often than would be expected on the basis of an accidental basis. So that suggests that there may be a level in between semantics and phonology, and this is what's called the lemma level in Lefert's model. Basically, a lemma is a syntactic node of a word. So it contains all the syntactic information of words, such as the grammatical word class, the gender, whether it's a count or a mass noun, all that kind of stuff that languages tend to grammaticalize. So what you can do with this picture naming paradigm is you could not only ask people to name the picture, but you could also ask people to name them with a phrase, such as, for example, de rode stoel, the red chair. Okay, so what people would have to do in order to be able to do this is to select the grammatical information, for example, the gender, in order to select the correct determiner in Dutch, because determiners are gender marked and the gender must agree with a noun referent. So these noun phrases can in fact be used to investigate the selection of syntactic features during lexical access. Now in Dutch we have two different genders, de and het, in the singular. However, in the plural, these two genders, or these two determiners, I should say, become one form only. So it's both for common nouns and for neuter nouns, the determiner de is used. So this is important because if gender effects are caused by gender congruency, they should be visible in Dutch in the singular, but also in the plural, since effects of gender congruency are caused by gender congruency. So according to the gender account. However, alternatively, if they are caused by determiner congruency, and this is something that was unknown until then, they should be visible in the singular, because there's a difference between the determiners in the singular, but not in the plural, right? Now we tested this and found that there is an effect in the singular, So participants were faster when the distractor word in a picture word interference paradigm had the same grammatical gender as the target object, and they were slower when this was not the case. However, in the plural, there was no such effect, and the interaction between number and gender congruency was significant, indicating that the effect in the plural is statistically a different effect than the effect in the singular. So that means that these results from noun phrase production in Dutch support a gender competition account, but not the gender account. And this has also been supported by other recent studies in several other different languages. So this is in the meantime, it's a well-known and established effect. And if you're interested in grammatical gender, I can direct you to this book, which will come out next year. It's now in production by my colleague Tanja Kupisch and myself. It's a handbook on grammatical gender and classifiers in different languages. Then the next step is morphological encoding. So once we have accessed and selected a lemma in the lexicon, which is, as I said, which occurs in a competitive way, then we have to start doing our form encoding processes. And there's quite some evidence also in terms of speech errors that for morphological representation, so for example, this is my favorite speech error of all times, they underestimated me. So this is, of course, a merge between misunderstand or understood and underestimated, but the merge does not occur at random places, but it respects the morphological boundaries of the underlying words, right? Other errors like stranding errors, for example, getting your nose remodeled. Here, somebody said getting your model renosed also respects the morphological boundaries. Now, if you look at neuropsychological patients, for example, patients with a spelling deficits, so-called graphemic buffer patients like PB, when they produce compounds like nightstand, but also many other compounds, it's interesting that they usually produce more errors towards the end of a word than at the beginning of the word. Now, what you can see here is that this graphemic buffer patient treats the compound as in terms of their morpheme. So they make more errors towards the end of the first morpheme, but then they go back to zero baseline almost and produce errors just as if the second morpheme were a different word. So this also shows that these patients are aware of the morphological components of words. When we used the long leg priming paradigm to investigate morphological priming, what we found was that compared to an unrelated condition in blue, this is this one. We had two sets of words or two sets of pictures like magpie and also other pictures, and the second set of pictures like coat. That the unrelated condition was, or I should say, a transparent priming condition like extra nest, magpie nest, and extra oog, which is a opaque word in Dutch, which is morphologically related to the target extra, magpie, that they both yield significant priming effect compared to an unrelated condition. If you look to the second set of pictures, we find the same effect for the transparent words like coat pocket for coat, but not for jasmine, which has phonological overlap with the target, but only this overlap is only phonological, not morphological. So this means that the effects that we found must be cannot be semantic, because there's no difference between semantically transparent and semantically opaque words. but it can also not be, it cannot be phonologically either, because there's no phonological priming effect. So these effects must be morphological, or they must have a morphological origin. These effects were also found in an ERP study that I don't have time to tell you about here, but we replicated these results also in a neuroimaging study behaviorally, and what we found in the fMRI data was in a conjunction analysis between the transparent and the opaque primes. We found increased activity in the left inferior frontal gyrus, more specifically in Brodmann area 47. And this may reflect an increase in allocated processing resources that had the effect of producing faster naming latencies. So with these data and also other data that I don't have time to tell you about today, it's clear now that there is a morphological component also involved in speech production. Oh. And let me go back. And we have recently also worked more on morphological encoding. For example, Jiaqi Wang, who just defended her PhD dissertation under my supervision at Leiden University a couple of weeks ago, did a lot of work on morphological compounding in Chinese disyllabic compound words, and some other work has also been published in the area of morphological processing from our lab. Okay, phonological encoding. We know that speaking is quite a fast process. We speak 8 to 12 phonemes per second approximately, which translates into 3 to 4 syllables per second. And we, under normal circumstances, we hardly make any speech errors. What my colleague Miranda van Turenhout did a number of years ago is to get participants name pictures, and at some instances she would present a frame around the picture, like you see the ice bear here, and then a rectangular frame appears after 300 milliseconds. And whenever that happened, participants had to do a dual task. And she was measuring an ERP signal from the two motor cortices, from electrodes C3 and C4. And so the dual task that people had to do was the following. So whenever the objects that they saw was an animal, they had to use their left hand to respond. When it was an object, they had to use their right hand. Okay, so they first have to make a semantic or conceptual differentiation between or classification of the object that they see. However, they only should press the button when the object name, the name of the object in Dutch, but it's similar in English, so that's practical for me, starts with a T. So for example, when like in tiger or table, but not when it starts with an S, as in spider or the Dutch word for shoe, schoen. Okay, so first you have to think, okay, which hand do I have to use? And then do I have to press the button, yes or no? Sounds complicated, it's very easy, I can tell you. What she did was she was looking at what's called the lateralized readiness potential. And she computed this by just collecting data from 2 electrodes, as I said, and then this readiness potential is based, this lateralized readiness potential is based on the readiness potential that you can measure whenever we make a voluntary movement. So whenever we, for example, press a button, there's already activity in the brain visible and measurable up to 1 second before we actually execute the action. So what she found was that compared to the go condition, so the go trials are the black lines, the straight lines, the no-go trials also increased in activity, so they deviated from the zero baseline for 40 milliseconds, and then they went back to the baseline. Okay, so this is tested statistically. So this is this effect that you see here. So this is the effect that we are interested in. So we are here interested in the Go trials. Okay, so that means that only after 40 milliseconds they realize that they don't have to press the button, because they went from the semantics to the phonology. What she then did, and this was very clever, was to use the final phoneme to make the decision. So now people only have to press the button when the final phoneme of the object name is an R, like in tiger, but not when it's an N, like in spin, spider, or schoen, shoe. Okay, so now you have to monitor the last segment of the word. And what she found in that condition is that the no-go LRP, so the dashed line that you see here, only went back to baseline after 120 milliseconds, which suggests that segments are planned, onset segments are planned before offset segments, and that there is a certain time course involved in phonological encoding. And that this time course is a serial one, as suggested also in the Lefeld model. So what we can do with this data is we can now estimate the planning time for each individual phoneme relatively accurately. So in order to plan one phoneme, we need about 15 to 20 milliseconds. Now, what I've shown you is lots of different approaches to speech production. You can measure behavioral data, you can measure electrophysiological data, neuroimaging data. You can look at neuropsychological patients who have language deficits, and what we then should do, and what Peter Indefry in this study has done, but only for neuroimaging results, is to put all these pieces together for the big puzzle. And if we do that, we can get a pretty accurate estimation of what's going on in our brains when we produce speech. So we can, for example, what we know now is that we start out activating our middle temporal cortex for semantic activation and lexical retrieval. Then we activate a part that's a bit posterior to that, close to Wernicke's area for phonological retrieval. We then send the information that has been gathered in this part of the brain to the front of the brain, to an area that's closely related to Broca's area for syllabification. And then we can finally activate our motor cortex to articulate what has been planned phonologically and phonetically. So with this, I would like to thank you for your attention. You can, if you're interested, you can download articles from my website. Also at my CityU Scholar website, they are available. And you can, of course, if you have questions, you can send me an email. Thank you very much. Compound words in Chinese are very interesting because they are abundant in the Chinese lexicon, right? And when I first heard about compound words, I was really fascinated by them, because I thought, okay, how do you guys, for example, say a goat in Chinese? It's a mountain sheep. It makes sense, right? And a train is a fire car. Yeah, it makes perfect sense. So lots of very transparent compounding takes place in the Chinese lexicon. Now, we thought when we do the same experiments that we did, for example, in German and also in Dutch, we would also get similar results in Chinese, right? But this was not the case. So the results that we obtained in Chinese were slightly different, both in terms of the role of what the components role was and the frequency of the components, there were differences. There were also similarities, but there were also fine-grained differences in the phonological or in the morphological encoding in Chinese when you compare this to Indo-Germanic languages like German and Dutch, for example. And this showed us that it's important to do cross-linguistic research, because only when you do cross-linguistic research, you can really get the full picture. So what we have been doing in our lab is lots of research also on other understudied languages. I wouldn't say that Chinese or Mandarin is still an understudied language. There's lots of research going on in Mandarin Chinese nowadays. But for example, if you take some African languages, some Southeast Asian languages, they are still understudied and under-researched. And you can really gain a lot of insights about psycholinguistics when you study these languages.
Thank you, Professor Schiller, for your inspiring talk. And let's give Professor Schiller another round of applause.